All right. Good morning, everyone. Thank you. Thanks to organizers for introducing, and thank you for coming early morning. Today, I'm going to talk about on the topic of meta learning within a lifetime. So let me begin with two common analogies of what people think of meta learning typically. So first of all, on the left-hand side, we have meta learning in the form of evolution. And the idea is that in the natural world, a species develop different forms over millions of years. And in machine learning, we have paradigms such as neural architecture search, meta optimization, hyperparameter optimization. And the common thread here is that the inner loop is often almost always the same task, and we iterate in the outer loop to change some outer parameters. And on the right-hand side, we have lifelong learning, where the agent starts from knowing almost nothing and starts accumulate its knowledge over its lifetime and accumulate different skills. And by the end of it, it learns a lot about the world and can learn new skills much faster and better. And in machine learning, we've seen like concepts like memory designs, few-shot learning, continual learning, and transfer learning. And they all trying to tackle in some aspects of this lifelong meta learning question. And what's common here is the task may change in the inner loop, or change or shift or grow over time. So on the right-hand side, this is what I'm going to talk about today. But you can imagine there will be some form of mixed meta learning that combines evolution and lifelong learning. So why should we care about the lifelong form of meta learning? So, everybody is very knows that there's a popular large language model out there. You can train it in offline data sets, and immediately it gets very well at deployment time. You can chat it with it, and then it can even have some personalized dialogue. Well, so the reason we need online adaptation is that eventually, as you interact with these large language models or chatbots more and more, you would like to develop a personalized knowledge, and it's not always efficient to have all the past conversation as its context. So some form of memory and parameter adaptation is definitely necessary in the context of chatbots. And for home robots, for example, the recently released Amazon Astro as well, right? So when you deploy this robot, it might ship with some initial knowledge, but when it's deployed in your home, you want it to learn continuously over time to recognize new people, new objects, and interact with you better and know you better. And in that scenario, I believe a lot of you might not want that data in your home, in your private conversation, to be uploaded in the cloud and trained together with other people's data. There might be privacy concerns, but one alternative is just let these robots to learn continually with you, and the data keeps in your home. So a lot of the historical meta learning paradigms, including few-shot learning, I would argue it is really belonging to the second analogy of the lifelong learning. But it feels like it does have flavors of this inner loop, outer loop meta learning flavor, right? So it starts from the analogy that humans continually learn new concepts and skills over the lifetime, right? And in fact, a lot of meta learning approaches, including, say, like the famous mammal and protonet approaches, does accumulate knowledge over time. So in mammal, you can accumulate in the parameter initialization, whereas in protonet, you accumulate in the learned representation space. But I would argue that standard few-shot learning is still quite far away from the ideal type of lifelong learning that we would like to test. And the reason is that the inner task is always like mimicking IID learning. You have like a support and a query. And outer loop is more like a domain transfer. So in the training time, you sample from a big data set of one distribution, and test time you sample from another distribution, and perhaps with some new classes. So here is a few points of, I think, what are the challenges of lifelong meta-learning. And first of all, there's the challenge of growing size of outputs, and not only these outputs are from new classes, they're also from the long tail distribution of the world, and you have to keep refreshing your knowledge of the rare things. And this is from the motivation of few-shot learning, and you would also want a memory module and incremental learning capabilities in those memoryless models, for example, the transformers and COMNETs. And secondly, there is the problem of changing distribution over time. So this is related to, say, like transfer learning, domain adaptation, but historically people have mainly benchmarking these algorithms in terms of source and targets, which I think we also need to look at more in terms of this online change of distribution and not just like from one to another. And thirdly, there's the challenge of having only a very small context window. So for example, in self-supervised visual learning, algorithms would benefit from a larger batch just to compare different instances of images with one another. And it will be challenging for this online form of visual learning where your context is really similar and correlated. And in this case, you might want to do some, for example, data replay to increase the diversity. So today I'm going to talk about a few points. First of all, I would like to talk about training data. So how do we make few-shot learning more continual and online? And perhaps going into the regime of egocentric videos, which I believe will be a really good playground for lifelong meta-learning. And I will talk a little bit about memory in terms of how to support incremental concept learning capability, and also the effect of small context when we train representations on lifelong videos. What's the effect of, say, batch size or data replay? And lastly, I'll talk about some thoughts on how do we really benefit from lifelong meta-learning. So all the previous points are like, how do we catch up on the IID learning, which I think we always treating IID as some sort of oracle, right? So in fact, I think if we can leverage the continuity and transitions in between the adjacent inputs, we can really benefit from the lifelong learning paradigm. So in the more recent work of few-shot learning, people have already starting to making few-shot learning more lifelong-like. For example, they can make a sequence of few-shot learning tasks and episodes, and by the end of the sequence, we would expect the model to perform well on all the episodes. And in our work, we also make an effort to make the sequence more online. And what's different here is that every input example could potentially represent a new class. So the model is essentially looking at one image at a time, and it has to decide whether this image comes from a new class or it comes from potentially from an old class. And we also want the overall class distribution to be not just uniform, but potentially represent a long tail distribution with some distribution change over time. And we also, let's see if the video is playing here. We also develop a more realistic online continual few-shot learning data set based on indoor simulators from Habitat. And the goal here is to recognize different instances in your home with a potential applications to home robot. So these are the few-shot learning examples, but there's also a whole bunch of egocentric videos, which I think will be very interesting next step applications for online continual lifelong learning, right? So you can really play with, say, like object detection or retrieval of historical video frames based on natural language inputs. And the image source may come from a robotic arm, may come from a car camera, or even more realistically, a human baby head-mounted camera, right? So basically, these videos contain all kinds of challenges in lifelong learning, right? And it's capturing the perspective of real-world agents. Essentially, we need an algorithm that can learn from this online stream, and essentially meaning batch size equals 1, right? And we want to train the representation, for example, and evaluate on tasks like instant recognition, object classification, detection, and segmentation. So you might notice that the actions are left out because these are pre-recorded videos. And ideally, if we want to learn lifelong agents, we would like to incorporate actions. But in these videos, you could still use pose and ego motion information as your source of training data. So next, I want to talk about memory, right? So we have those online continual future learning data. How do we use online memory to keep accumulating knowledge? And we develop a really simple model here, right? So the idea is that if we extract the input frames into some representation space using models like a CNN, and the idea is that we can store the embedding of each input into a prototype memory. So this is strongly inspired by the prototypical networks, but we make it online. So you can do the online averaging, right? So if there is a class label, you can simply store the embedding as an average. And if there's not, you can store it to the closest prototype up to some distance. If it's too far away, you just ignore it. And I should acknowledge there are other forms of memory. For example, in 2016, there was the memory augmented neural network, which is also similar to the differentiable neural computers, which are general forms of memory, differentiable memory. And there's also, say, like online MetaLearning, where the memory is stored in the parameter space and doing this gradient descent over online. And more recently, there's something called layered distributed memory, where you basically combine memory within your COM nets. So they have these COM LSTM blocks and going layer by layer. So the memory is essentially distributed all over your representations. So in terms of performance, at the time of the paper, we were able to significantly beat the former of the two memory designs. And the last one came after our paper, so it did show some win over our approach by having this deeper representation of memory space. And here is a short video showing how it really works in the what we call the roaming rooms environment, which is the indoor simulator environment of recognizing different objects. And you can see it make predictions of unknowns, but the next time it sees the object, it can memorize what was the label that was given to the agent. So future learning is really nice, right? So we can incrementally learn new things as we roam around the world. But oftentimes when we learn, we don't need label data at all. So this is, again, with the motivation of self-supervised learning, how can we remove the reliance on label data? And the intuition is that the categories should basically emerge by grouping similar items together. So when you go into a grocery shop, right, there are all the items being grouped together on the shelf, and you immediately try to group things together to form this concept of categories. So early literature in psychology also studied this, but there was no representation learning at the time, so you basically just grouping the attributes together. So continuing our work on online prototypical networks, we also developed online unsupervised prototypical networks, where the idea is that we can really learn this prototype memory without using any labels ever, right? So what we did is we developed a mixture model of these categories, and the core idea is very simple. So we store this prototype memory in the form of clusters, and there's just no wiping of clusters one after another, right? In order to make sure that we don't explode the memory, right, we're going to recycle the smallest cluster, and the cluster size is going to decay every time step. So this represents some level of simple form of forgetting in the memory. And we can run EM to determine the cluster membership. And if all the clusters are far away from the current input, we're simply going to create a new cluster. So all of these are automatic without relying on any external labels. And the learning objectives is really inspired by self-supervised learning, where we create augmentations of the same input image frame And we say that the augmentations of the same frame should really stay in the same cluster. And we control the marginal probability of creating new clusters to prevent everything belonging to one cluster, or we create every single new cluster for each frame. And here are some experiment results. We tested both on unsupervised evaluation, where at test time we also don't give the model any label, or supervised evaluation, where at test time we give it labels and it does more supervised clustering. And what's interesting here, we're actually having a very close performance compared to online proto-nets, which are trained using supervised episodes. So this is very encouraging, meaning that we can learn these prototype memory models without actually leverage any class label during training time. And we also tested to compare with some of the more classical self-supervised learning methods, and we found our methods is also having a boost compared to these baseline methods in these online representation learning environment. So next I'm going to dive a little bit more into these results in terms of the comparison with self-supervised learning, and with the goal of understanding the sample diversity within the context. So self-supervised learning typically relies on a sample diversity in a batch, so that we can distinguish one image to another image. But for lifelong learning, right, samples are typically from highly similar windows of these videos. So the question here is that does the self-supervised methods do well in these environments? Does methods that don't require negative samples perform better? Right, so here we did experiments where we tried to understand the effect of batch size, and we varied a number of frames, the context window, for each of the methods, right, including sim-clear, which is contrastive-based methods, and swab, which is clustering-based methods, so it's more similar to our methods, which is also clustering-based, and SIM-CM, which is a method that doesn't rely on negative samples. Right, so what we found is actually sim-clear is actually performing the best across these self-supervised methods, right? Although there is the concern that negatives are too similar for sim-clear, but it turns out it's still better than swab and SIM-CM. And for MoCo, we also tested later, and it does better than sim-clear because it has a queue buffer of representations that allows it to store more things from the older context. And our unsupervised proto-nets does better, and our hypothesis is that it can dynamically create clusters online, so you don't have to subject to the constraint of you have equal clusters and have a fixed number of clusters. And I just want to mention there's another recent paper that's also trying to benchmark these self-supervised learning methods in those baby cameras. And they've also found similar conclusions where sim-clear, those that explicitly use negative samples, or say like Barlow twins that explicitly encouraging diversity among samples, does better than approaches with no negative samples in online video representation learning. So another thing that was interesting when we try these is the effect of the natural replay from the world. So typically when we do continual learning, we try to make the task one after another without any replay, so that we will force the model to do its own replay or force the model to show really strong memorization performance. But the world is basically naturally providing us replay. So when I get up, I eat breakfast, and then I do a walk, and then I eat something else, right? So I'm constantly trying to review the old task that I did before. And what we found in this recent paper, that we try to understand the effect of forgetting and replay in like a supervised setting. What we found is that the forgetting is indeed very large, but these recoveries are even more dramatic. So if we train a network for a period and then train the older environment, it gets a dramatic recovery. And this suggests that networks could take advantage of the natural replay in the world, right, in order to consolidate knowledge. And thirdly, I want to talk about how can lifelong learning outperform IID learning. So previously, we're kind of always chasing after IID learning, right? There's all sorts of challenges in self-supervised learning. IID is still better than online representation learning, right? So what I would argue is that we should focus on how to leverage the continuity and temporal correlation from the physical world, right? So the model should be able to leverage relationships across, say, like a pair of adjacent input in terms of the actions, change of pose, and movement of pixels. And it can also leverage information across a longer time range. For example, we could propagate the uncertainties and consistencies over a longer range of video frames. However, people would say that nothing really prevents us from using a very large IID batches of video clips. But when you try to do that, you already enter the regime of lifelong learning. So you're basically saying the model is having multiple lives at the same time, and perhaps this batch size is just going to improve your speed of convergence. So here, this is a disclaimer. The work isn't really a form of meta-learning, but I would like to show a use case how we can leverage the continuity in between input frames to achieve better performance, right? So the key idea here is that when we have two input frames, right, we can run an optical flow network, which is trained offline from simulation environments, and to basically discover the movement of pixels or the pixel correspondence between the two frames. And we follow this BYOL paradigm where this online network and a target network each produce a dense spatial representation over spatial locations. And the training objective is simply that we try to transform one representation using the input optical flow to another space. And then we use this normalized mean square error loss to train the network to learn good representations. So the idea is very simple. It basically says that regions that move together should contain consistent representations. And here I'm showing you a visualization where we train the representation from a large unlabeled data set. And now we read out the representation on Cityscapes data set with an additional linear one-by-one convolution. And you can see that representation already contains a lot of semantic information. And if we fine-tune the network with a small amount of labeled data, we can really show the benefit of this online not online, but representation learning leveraging adjacent frames compared to just pure end-to-end supervised learning. So as a summary, so in this talk, I introduced meta-learning within the lifetime as opposed to meta-learning over lifetimes. And the goal is to continually learn through a lifetime amount of data. And I say that online continual future learning and egocentric videos are basically our playgrounds in terms of understanding the challenges and opportunities in meta-learning. Where there's challenges that we have less clean data than IID environments, right? We can also have a lot of opportunities in terms of design memory components that facilitates incremental growth of concepts. And we can also understand how data play really benefit models and how do we perform online clustering to capture the online nature of the data and the imbalanced distribution. And lastly, the opportunity lies in that we can leverage the information across different inputs, for example, the continuity in between inputs, And for vision people, this means, say, like optical flow, motion, etc., to really benefit from lifelong meta learning. So that's the end of my talk, and thank you for your attention.